All right, honors kiddos, let's get started on the stuff that is going to separate honors from CP. We're going to talk a little bit today about expanded valence and about hybridization of molecules. And that sounds like some really hard stuff. It's really not that bad. Moderate complexity. I think we'll get through it okay, though. The first thing is you want to make sure that you've got all of this good stuff out, your table. So before we had this simple table, okay, where we had from 2 to 4 electron pairs, what we're going to do today is stuff that involves from 5 and 6 electron pairs. Now you may be thinking to yourself, well, how can I have 5 and 6? Because I'm looking to get the octet rule, which would be 8 electrons, which would be 4 pairs. Doesn't seem possible that I can have 5 and 6 pairs. Okay, well, here's the deal. There are always exceptions. This is true pretty much all the time in English, in history, in science, whatever. There are always some exceptions to every rule. So here's the exception. If an element is in period 3 and below, it can have expanded valence. Now, what does that mean? That means typically that it can have 10, 12, and in some really rare cases even 14 electrons around the central atom. Now, don't let this blow your mind because it doesn't happen that much. You'll know it when you get to it. When you start to draw a molecule and you just can't fit only 8 and still make everything bond, it's got expanded valence. So just real quick, remember that this is period 3. Okay, so it has to be something below this blue line, basically. Usually the way it's going to work, you see a lot of these two, phosphorus and sulfur, and then you see a few of these. It can be anything, but it's generally these things. Okay, and that's the stuff that we're going to work with today. So let's see how a couple of these set up. The first one is phosphorus pentafluoride. And so we're going to draw the Lewis dot structure for this. Okay, phosphorus has 5 valence electrons, and we've got 5 fluorines. Okay, and each fluorine, remember, has 7. And so we've got 5 of them. And you can sort of see as we're starting to stack these up that I am not going to have enough single electrons, really, to make this happen. Okay, so if I start drawing the bonds, I've got a bond there, and a bond there, and a bond there, and I've got all the singles, and I still have 2 fluorines that are unconnected. So here's what happens. They bond here. Okay, and that leaves me with a molecule that looks like this. Okay, so you're like, well, all right, I'll buy that. I mean, the fluorine's obviously got to connect to the central atom. But if you count around the phosphorus here, it's got 2, 4, 6, 8, 10 valence electrons, which is more than what we can normally have. Normally, we only have 8. Okay? Just go with it. If you happen to end up with 10 or 12 and it's something that's below period 3, meaning that it can't be carbon, okay, or oxygen, then we'll sort of go with it. Most of the stuff we're working with is carbon, but if you get one of these, just go with it. So then the question becomes, what then is the shape? So that's where the second part of the table, or the back side of the table, comes into play. So if I look at this, I've got 5 electron pairs, and they're all 5 bonding. Okay, and that's what we got. So my shape in this case is trigonal bipyramidal. And if you look on the webcam here, you're going to see the shape of that molecule. And here's what it looks like. You kind of got a big line going down the center there, like one big y-axis, and then you rotate around and you've got 3 of the other fluorines in a plane together. And the reason it's called trigonal bipyramidal is that I can draw one pyramid on the top and one pyramid on the bottom. So it's bi, meaning 2 pyramids drawn on the top there. Okay, so that's the shape of that molecule. Okay, we're going to do a couple more just to see what these other shapes look like real quick. So I'm not going to draw out the whole thing. You can sort of figure these out. The next one is sulfur hexafluoride. Hexa means 6. We'll learn that in the naming section next. So I've got 6 fluorines. This stuff's some pretty cool stuff. You can look up on Mythbusters, sulfur hexafluoride gas. Guys give themselves some really super deep breath. Like helium gives you a really high voice. Sulfur hexafluoride gives you a really super deep, demonic, typo negative singer voice. So this is what sulfur hexafluoride looks like. If you look in the again, in the webcam, you see this molecule. It looks sort of like the previous one, the phosphorus, except I've got 4 in this plane in the middle instead of just 3. Okay, so we can rotate around that plane. Otherwise, it kind of looks almost the same. This is called octahedral because if I drew sides on each plane here on the triangles, then I would get 8 sides on it. So it's going to be octahedral. And again, how do we find that out? Well, we just looked at our table, okay? And I've got 6 total electron pairs, 6 bonding pairs, so I get octahedral in this case. Now, that's what you get if all of the expanded valence is bonding, which is certainly not always the case. So let's look at a couple of cases where that is not true. A good one is bromine pentafluoride. And so here's what happens in bromine pentafluoride. Got a bromine, okay? It's got 7, okay? And I've got my 5 fluorines. Now I'm not going to completely draw out these fluorines just for the sake of time here. But if I drew them all out, they all have 7 valence electrons. And here's the way they work. They all bond to these electrons on bromine, which makes pretty good sense. But now I also have a lone pair, okay? So when we go back to our chart, all right, I've got 6 total pairs, but only 5 of them are bonding, and I've got 1 non-bonding. That leads us to a pretty cool little shape called square pyramidal. And again, let me pop up the webcam here and sort of show you what that particular molecule looks like, because I think it looks pretty cool. You'll notice that it has sort of the same as the octahedral shape of that sulfur hexafluoride, except the bottom's cut off. There's no bottom thing here. And so it's called square pyramidal because the bottom is a square, okay? And then if we drew that square up to the top, it would form a pyramid up at this top chain here. So it's called square pyramidal, a pretty interesting shape. Now, why does it look that weird? Well, because this bottom area where we had the other fluorine in the sulfur hexafluoride, there's just a lone pair there. It's still important. It's still forcing the shape, okay, Vesper-wise. It's still forcing those other pairs up the way they ought to be, but it's not actually making a bond in that particular case. All right? So let's do one more of those real quick, just so that you get a good idea of these more complicated ones. And again, we're going to use the chart for most of these. And when we get closer to EOC time, we'll prep a little bit more for the stuff that's really sort of out there. So sulfur tetrafluoride looks like this. And again, if you want to go back and draw all the bonds, that's fine, but I'm trying to keep these videos a little short, so I'm going to draw out what this molecule looks like. It looks like this. Makes pretty good sense. Oh, sorry, actually, I messed that up a little bit. Sulfur has 6 valence electrons, so it ends up looking like this. Somewhat similar to the last one in that there are mostly bonds, and then there's 1 lone pair, okay, lone pair right there. And so if I go back and look at my chart, I've got 5 total bonds, okay, so 5 total bonds, but only 4 of them are bonding. 1 is non-bonding. You see it leads us to this really interesting sort of shape. It says it's called seesaw. So let's look real quick and see what that looks like, because that's pretty interesting. Here's the reason it's called a seesaw, because if you look at this, there's sort of like these 2 legs supporting it, and then we could sort of seesaw the molecule one way or another. It could bend. The seesaw could go down or up. Looks pretty weird. And again, it's very similar to the trigonal bipyramidal that we had for the phosphorus pentafluoride, except that the top part's cut off. What's in the top part there? Remember, that's where that lone pair is, and that's what forces it down into this different shape. You can see that we've got some other weird shapes. We've got T-shaped. We can even have linear. If you've got 5 pairs around the center, but only 2 of them are bonding, everything else is non-bonding, that forces it into a linear shape. So you can see that we have all these sort of different kinds of shapes. It's really no harder than what we did before. It's the same basic principle. You're going to draw it Lewis structure-wise, and then you're going to go through and look at your table and see what it looks like. Okay, so let's talk about something a little bit complicated that students occasionally have some problems with. That is the idea of hybridization. Now, when you talk about hybridization in biology class, hybridization means that you had basically a blend of 2 different kinds of traits. So if you were talking about like genes and genetics and Punnett squares, you had, like, say, a white rose and a red rose, and you blended them together instead of one being dominant. They hybridized, and so you get a pink rose out of it. And that same thing is going to be true here of electron models. And the reason that we do this is because that when we actually do our empirical data, because science is all about actually experimenting and doing the data, what we should get is that if we've got something like a carbon here, okay, so here's carbon's electron structure, or electron configuration. I've got 1s, 2s, okay, 2p. I've got 6 total electrons. My valence is right here. These are my 4 valence electrons, so that if I drew my Lewis dot structure, I get this. Okay, that's these 4 electrons. But the way this works is that, okay, so carbon can form 4 bonds, but really, if that happened, the p bonds should look a little different than the s bonds, because p orbitals look like this and s orbitals look like that. And so they should form different bonds. What we actually find, though, is that in a methane molecule, which is sort of the classic example of this, that's not true. All of the bonds are exactly equal. So we sort of need some way to make that work. Like how exactly does that actually work? We know that that's what actually happens in the real world, but how? So here's the way it works. We've got 2p, and we've got 3 orbitals, right? And we've got a 2s with 1 orbital. So what we're going to do is we're going to combine those 2 orbitals into one super subshell called an sp3, and it's called an sp3 because there is 1 s and 3 p orbitals, and that means that I have 4 boxes altogether. Now, what does that mean for our carbon, and why does it lead to the structure that we get? Well, because if you remember, what we had is we had 1 s, and then this would be the 2 sp3, and so we got 6 electrons. I draw them here. And if I get up here, then Hund's rule says that if the S and the P3 are all together, then I actually separate them. And instead, I've got 4 single electrons instead of the 2 paired and the 1 unpaired that we had originally according to our normal model. And this kind of makes sense because, again, if I draw the Lewis dot structure for carbon, I have 4 single electrons, and that directly reflects what's going on here for hybridization. Okay. So how do you know what the hybridization is? Because you may have questions that say, what's the hybridization? Okay, it's actually pretty simple. If we look back at our charts, okay, they've all got the hybridization listed. Okay, so sp3 and all that stuff. But you're like, oh my gosh, do I have to remember one more thing off that chart? There's a lot of information there. So how do I know all this? Okay, well, let's make it pretty easy. Here's the way hybridization works. If I have 4 electron pairs, which is normal, that's the octet rule, right? 4 pairs is 8 total electrons, then the hybridization is always sp3. Okay? If I have 5 pairs, like in the case of our phosphorus pentafluoride, then the hybridization is called dsp3 or sp3d. Okay? And what happens there is that I've got 1, 2, 3, 4, 5 places to put my electrons. I steal 1 box from the D's. So I've got S, P, 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 and 1 from the D's. Okay? As you might imagine, 6 then is going to be sp3d2. Okay, so 1, 2, 3, 4, 5, 6. 2 from the D's, 3 from the P's, 1 from the S. We can actually have less than 4. Again, just like we can have expanded valence, we can actually have sort of shrunken valence. We can get sp2 where we've got 1 s, and then we only steal 2 from the p's. Okay? And if we only have 2, then we would have sp. Okay, 1 from the s, 1 from the p. So our normal, what we have most of the time is sp3, where I've got 3 from the p, 1 from the s. This is kind of what we should normally sort of look out for right here. Okay, but we can have any of the others. Now, how does this come into play? Why am I going to need to know this on the EOC and all that jazz? I would say don't stress about it. In the honors test, there's usually 1 question each year about hybridization. And all they're going to ask you is they're going to say, hey, given this molecule, what is its hybridization? So all you have to do is the same thing we've been doing, okay, where you just draw the structure of the molecule. So like say they give you BF3. Okay, and they say, what's the hybridization? Okay, so you start to draw that. You say, okay, boron, hold on. I don't do a lot of boron, so let's go back and look at the periodic table. Boron right here. Okay, 1, 2, 3 valence electrons, right? Okay, so 1, 2, 3. Already I know I'm going to have some issues, right? That I'm not probably going to have a normal molecule, that I'm probably working on an exception. How do I know that? Because seems like that would normally form an ion, and it does sometimes, but it can also form covalent compounds. Okay, so we got our fluorines here. So we bond, 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 and there's really nothing else I can do. There's no other thing that actually happens here. So I've got 1, 2, 3. Okay, 3 pairs. So that means 3 pairs is sp2 hybridization. So all you have to do is draw it. Once you get it drawn, then you should know it's one of these. There's only 5 options. Most of the time you get this. Occasionally you'll get one of these 2, and very rarely do you get these. Shouldn't get too many of these because modern science actually says that it probably doesn't hybridize with these, but sometimes that still gets in there through some of the old books.